Okay, so we started talking about this idea of minimal sufficiency, if you recall. The point was that sufficient statistics are not unique. To remind you, the data itself is sufficient. So we went on and asked if there is a way to characterize the smallest sufficient statistic. And that led to the idea of minimal sufficiency, which is also motivated by this lemma that if you have T sufficient for a family of probability distributions or for a model, basically, then if I can write another statistic S as a function of, if I can write T as a function of S, then T has to be, so we have a sufficient statistic T. If I can write T as a function of S, then S has to be sufficient because applying a function reduces information. So then we use this as a basis of our definition of reduction. So if I have a statistic which is sufficient and is also a function of any other sufficient statistic. So imagine this T, it's itself sufficient, but for any other sufficient statistic, I can find a function that reduces it to T. Then you can say that T is like at the bottom of that hierarchy. So that was the definition of minimal sufficiency. T is sufficient, and T can be written as a function of any other sufficient statistic. That was my notation for T being the function of S. And so we sort of, towards the end of that, the last lecture, we sort of argued that if you look at the likelihood ratio, so if I have my probability densities, and if I, let's say, divide them by the probability density at a particular fixed parameter, that would give me the likelihood ratio between, for comparing, let's say, model based on theta and the model based on theta naught. That likelihood ratio for a fixed theta and for a fixed theta naught is a function of x. So formally, it's a statistic. So a statistic is a function of the data. So for any fixed theta and theta naught, that gives me a statistic. And then if I collect them into a vector, or in general, if the parameter space is infinite dimensional, like continuous, this would be a function. If I look at that vector or the function, the point was this is going to be minimal sufficient. So the way we tried to argue this is, first we showed this result that in a DCS family, again, this is a technical condition dominated with common support. We'll get back to that at some point. In a family like that, the following or equivalent U is sufficient, basically, if and only if this relation holds. Okay, so it means that L theta can be written as a function of U, and this should hold for any theta. So these likelihood ratios would have to be a function of U, and we did the argument in one direction. That's an easy consequence of writing down the factorization theorem and basically dividing. We get this functional form, so this can be L theta can be written as a function of U of x. And if you reverse or backtrack this argument, it gives you the other direction. And then we use, so just a little bit of manipulation on this. We said that, okay, I'm gonna write everything here in a different format, so I can concatenate everything in, or like just put together all the L thetas into that vector or function. So this is sort of equivalent to this entire function or the vector being less than or equal to S. This is the little argument there, sort of tautology again, to some extent, at least if things are finite, the parameter space is finite, it's tautology. So that's another statement of that fact. U is sufficient if and only if this likelihood ratio function, or if you want to call it likelihood ratio vector, is a function of U. And then you can apply this result to the L itself. So I can plug in U equal this bold L. And you can see that B holds trivially, L is a function of L. So A has to hold, so L is sufficient. So then we get the conclusion that L is minimal sufficient. The reason being that L itself is sufficient by this result. And by part B, or basically A implies B, any sufficient statistic U that I have, L is a function of U. Okay, so these two together imply the two conditions of minimal sufficiency. So we proved that L is minimal sufficient. Again, the argument is here. So let U be a sufficient statistic. A implies B, that lemma means that L can be written as a function of U. That's the first condition of minimal sufficiency. And then we also know that L itself is sufficient because L satisfies part B with U here, so L has to be sufficient. So these two conditions are satisfied. So L is a minimal sufficient statistic. Okay. That's like a short proof, basically manipulating a bunch of. The only real result was this lemma 2. The rest is just arguing from this. Okay. Questions? Comments? So this is a nice result because it just sort of solves the problem of minimal sufficiency in a satisfactory manner. We just have to form these likelihood ratios, and at least theoretically we have a minimal sufficient statistic. You might not like the form of it, but okay, let me like build towards that. So one consequence of that, if I want to show a statistic is minimal sufficient, is this corollary. T is minimal sufficient if T is sufficient and T can be written as a function of L. So is this true? If you believe that L is minimal sufficient, is this? This is actually true if I replace L with any minimal sufficient. So this is saying if you have a minimal sufficient statistic, if you want to show something else is minimal sufficient, it's enough to show that T is sufficient and T is a function of that minimal sufficient statistic. Is this true? Why is it true? So there are two conditions for being minimal. One is that T is sufficient, so we are assuming that. The other one is that T is a function of any sufficient statistic. So does the second one give you that? Yes.
So L is a function of any other sufficient statistic, so T is a function of all of them.
Yes. Right. So if you have basically this also any minimal sufficient, so because this is minimal sufficient, it's a function of any other sufficient statistic. So now if I have a statistic, it's a function of that by function composition. So it's going to be a function of any other sufficient statistic. Okay. So this gives you one way to try to show sufficiency. So it's enough to show that T is sufficient, which is usually easy by factorization theorem. And also if I can write T as a function of L, then I would be done. There are various reformulations of this. So this guy, T less than or equal to S, if you ignore the almost everywhere business, this is saying that there exists a function F such that T can be written as a function of L. Okay, so this requires you to show a function. I can sort of eliminate the function here because I don't care about the actual function. I just want one function to exist. So the existence of a function such that this holds can be equivalently written as these bullet points. So that statement is equivalent to saying that if I apply L to two data points X and Y, and if it's equal, L, like the value of L on these two data points are equal, then T should assign the same values to X and Y. So if this implication holds, so this is saying basically for every X and Y if you want. So it's a conditional statement. If whenever this holds, the other one has to hold. If you think a little bit about this, this is equivalent to there exists a function. Remember, there's the sort of a idea that if this holds, for example, and this doesn't hold, right? He can discriminate between X and Y, whereas this guy can't. So once you move from X to L, you lose that distinction of X and Y, and so T cannot be a function of L because T is distinguishing between X and Y. So if you think a little bit about that diagrams that I had, I'll let you think about this. So you have another one here. So there's a function from X to some place which is L, and then you want to go from L to T basically, or sorry, this would be T and then this would be L. So think about this. We can go through it, but I'll let you figure this out for yourself. It's rather easy. The idea is that if L cannot distinguish two data points intuitively, T shouldn't be able to distinguish because otherwise you would have more information. This you can also is like the equivalent state in terms of the level sets, often not realized by people. Someone in this class actually previous years pointed this out. Level sets of L are included in level sets of T, sort of. Level sets are the set of all data points that go to a certain value. Okay, so basically the set of all X such that L of X is, let's say C for a particular constant, that would be the level set of L at level C. So this set is included in one of the level sets of T. So it's roughly the same thing as this. So for all the X's here, L assigns the same value. So all those X's have to be assigned the same value by T. So they belong to some level sets of T. So there's an inclusion of level sets. Again, this notion of refinement of information is captured by the inclusion of level sets. Another way of saying is that level sets of T are coarser than the level sets of L. So so think of the how should we think of it? Yeah, so roughly saying if this is maybe the level sets of these are the level sets of L. The level sets of T should be, for example, like maybe T would like combine these two level sets. So these would be one level set and the other one would be so this is the kind of picture. So it loses some information. That's sort of the idea, okay? Level sets of T. That combines these two inner level sets of L. So these are just like mathematical ideas to think about. It doesn't matter as much, but the main point is that I can replace, for example, this condition here with any of these. For example, if I replace this T function of L with this, I get a result like that. Immediately I get this another curl. So T is minimal sufficient and only if T is sufficient. And whenever L assigns the same value to both X and Y, then this implies T of X is equal to T of Y. This is sort of a version of this appears in Keynote, for example. This is nice because there's no reference to any function. So you just have your likelihood ratio, let's say, and you also have you're a statistic and you can verify the second one. If you want to go further, I can actually replace this with the other direction. So I can just remove that A. And if this holds, I'll let you think about it. So heating sufficient from the very first memo that you showed is equivalent to okay, maybe just mention it. So heating sufficient is equivalent to L in the function of T. So have L a function of T and T a function of L, so they have to be basically a bijection of each other. But that's what it says. So in the end, either you go with that, usually it's easier to verify sufficiency, but if you don't want, this is also true. T is minimal sufficient if and only if this holds, but this just means that T has a bijection to L, which we already know. If you have a minimal sufficient statistic, you're going to be minimal if and only if you have a bijective relation to the minimal one. So there's nothing new here. Another thing that we can do is that we can replace this L of X equal to L of Y with this notation, which is what Keener uses. So that I just want to mention. You can get like basically 10 different versions of the same thing in different, if you write it different. So P of this notation is P theta of X. So remember, if I look at this density as a function of X, it's a density. If I look at it as a function of theta, it's the likelihood. So usually write this as L sub X of theta because we're now looking at it as a function of theta. It's the same thing, just the notation reinforces the idea that we're looking at it as a function of theta. So this is the likelihood, and the likelihood ratios being equal. So this is saying likelihood ratios being equal for observations X and Y. This is equivalent to saying that Lx theta is proportional to Ly theta, where proportional means as a function of theta. So I hope this is clear. So when you write it as like this, these are functions. It means there is a constant. Basically, there exists a constant C such that, let's say, positive, such that Lx of theta is C Ly of theta for all theta. So that's the meaning of being proportional. So up to a multiplicative constant factor, the likelihoods are the same. Okay, like 2 times that, or so this could also depend on X. Sorry, yeah, X and Y. So if you want, yeah, let's do it. It doesn't depend on theta, but it could depend on, given you precise, could be dependent on X and Y such that Lx theta is Cxy Ly theta. Okay, this should roughly be clear because L of X is just P theta of X divided by P theta naught of X, which is just Lx theta divided by Lx theta naught. And when you set this equal to the corresponding statement for Y, you can see that these this behaves like a constant in theta, and the corresponding one for Y behaves like a constant in theta. So you rearrange, you get this relation, where this would be just the ratios of those 2 constants. So this is, for example, what Keener does. So what Keener has is A, and then in place of this, replaced with Lx theta proportional to Ly theta. So that's one of the, I think, theorem 3.11 in Keener. So if you understand what we talked about, that's just equivalent to what I mentioned. So that would be like B and AT is sufficient. So this would be like this if and only if this is theorem 3.11 in Keener. Okay. So informally, what this is saying is the shape of the likelihood is minimal sufficient. Okay, shape means up to a constant factor. Okay, like I don't care about the factor, but as a function, I think this is what Keener says, shape of the likelihood, whatever you want to interpret it, as long as you understand what you're doing. Likelihood sort of is minimal sufficient. Okay. We'll see some examples. It's a little bit abstract. I just want to say that these are like, you might see this in various formats as long as you understand what you're doing. Basically, everything is like the only thing is something like this. And this sort of follows from factorization theorem. Once you have this, then the rest follows. Questions? Okay. Let's see an example. So we have the Gaussian location family, and if you recall, the setting is that we have IID observations from this density, which can be written as like a base density, which is this guy shifted around. Okay, so the idea was this is like a base shape around 0, and just these would be shifted versions of it. So I'm just gonna shift this to location theta, the same shape. So that's basically my theta. So it could go around, but it remains a Gaussian. So this produces, if you are comfortable with the Gaussian distribution, this family is basically a normal location family. It's like saying x1 up to xn are IID. And from a normal, it means theta and some variance. I don't know, call it C prime, just some variance. The variance is known. So actually, you can figure out what the variance is. Anyone knows what the variance would be in terms of parameters that I have here? Sorry. So this would be like 1/2 sigma squared. Remember. So 1/2 sigma squared. Right. Yeah, so that sigma squared would be, what would be sigma squared? 2 beta, 1/2 beta, right? Okay, so that's the variance. I usually like write the variance here, not the standard deviation would be what you mentioned, but 2 beta. So that's assumed known. So the only parameter is theta. So that's our parametric model. So this is known. So now, how do we calculate or like use this theory? I'm going to calculate the likelihood. You can see that the likelihood is just plug this fx into the p theta. That will be the likelihood. Let's maybe do it. I have to do it here. So we were saying is like p theta is so p theta of x is just proportional, right, to e to f of basically x minus theta. It's actually equal to this, but this is proportional to x minus beta. Okay, I'm going to do xi here because that's one of them. Xi squared. Xi minus theta squared, right? And then p theta of x usually is like the vector is product I from 1 to n, p theta of xi, and it's going to be proportional to x negative beta summation I from 1 to n, xi minus theta squared. Again, because we care about the likelihood, we don't care about the normalizing constant. It depends on beta, but beta is known to us. So this would be also Lx. Yeah, I shouldn't have written. So this is proportional in theta, not in x. So in the end, this is going to be L theta. Sorry, not L theta. Lx theta. So that's my likelihood. Lx theta is equal to this, proportional to this. And then you do some expansion. You get this part would be xi squared minus 2 xi theta plus theta squared, right? And then I get summation. And then you expand. So you get e to the negative theta times the summation here. X minus beta summation I xi squared plus 2 beta summation xi theta plus or minus n beta theta squared, if we haven't made any mistakes. And then what I'm saying is sort of, I can discard this term, right? I can write something like 2 beta, yeah, just do summation xi theta minus n beta theta squared. So why can I ignore that term?
It's not a function of theta.
It is, so yeah, it's not a function of theta, but I have to like make it, I can discard like multiplicative factors, right? So this because of the exponential, this would be exponential of this times exponential of this. So exponential, so there's e to this guy right here. And that's a constant. So I can, it's like a factor here, which is constant, so I can drop it. I can't drop like additive terms, but it's inside the exponent. If you take the log of this, which is the log likelihood, you can drop the additive. So you have to be additive, like up to an additive shift in terms of the log likelihood, or multiplicative shift or factor in terms of the original likelihood. Okay, so that's the sort of, here, if you want, I can take the log. So it doesn't matter if I take the log, because do I lose information? So what it's saying is that the result is saying is that basically, so our theory is saying that like theta maps to x 2 beta summation xi, this function, the entire function is, if you plot it as a function, this function is minimal symmetry. Okay. And I can do various things. I could have looked at the log likelihood, right? Log L x theta. So if I take the log, I could say that maybe this guy so our theory says that the following function is minimal sufficient. I can also claim that this is minimal sufficient. Why can I claim that?
It's still just a function of it.
If it's a function, it's not necessarily, you could lose information if you apply a function. There's a particular kind of function.
Well, that and then the input is also minimal sufficiency, right?
So this is minimal. I can take a function, let's say the function that maps your constant. Not every function would work. What do I need to have? Monotone. Basically bijection. So you need a one-to-one correspondence. So this log, because this is an the density or likelihoods or densities are non-negative. So log is non-negative. Sorry, log is monotone. 1 to 1 basically, a bijective map between 0 to infinity to 0 to infinity. So if I take the log of this, I can take the exponent back to get this. Okay, so I don't lose anything. I can recover this from that as a function. There is no loss of information. I can, for example, multiply it by a negative sign. Like x map to negative x is also 1 to 1. So let's say this is also, I think I have this up there. So this would be minimal sufficient as well. These are all okay. But it might not satisfy some of you that this function is minimal sufficient. There's something simpler here, which is minimal sufficient. Which maybe you guys can help me. I need to be able to recover this entire function. So can you give me a statistic which is in bijection with this entire function? Here's the deep fact comes in, which is not that obvious. Like the difference, once you understand this and the difference between the L1 case, there's something going on with the likelihood of the Gaussian that makes this. I don't need to keep this the entire function. There's little information in keeping, like this has infinitely many points. I don't have to record all for all values of theta. Yes.
Is it if you have the total and from that, like some of the xi's from that, you just get very mean from that.
Great. So I can this is where the data comes in. And I can, if I have this, I can reconstruct this function. Okay. If I have the sum of xi, I can reconstruct the function. In the other direction, if you give me this function, can I recover the sum? I'll give you a plot of it. This would be a quadratic as a function of theta. It looks something like that. I give you the function, and you recover from the function the summation of xi.
You just need to know its roots.
Yes. So okay. For example, you can set the derivative. Yeah, it's roots or there's are there roots actually? Yeah, maybe it looks like this. There's like you just need actually like the location of the minimum. So for example, if you set the derivative to 0, if you take the derivative of this, the location of this will give you information. So you know beta, and you know n, the location of the minimum gives you. So the derivative of this contain the information, right? The roots are probably going to have probably a midpoint between. Is that true? No. Yeah, it could have like 0 roots, right? It could be like there's no real roots, but the minimum, take the derivative is equal to 0, that will give you. So I know once you give me the function, I know this location. So there's a bijection between this function and the summation of xi's. So xi, this guy is minimal sufficient. We didn't actually need to do the bijection. One direction is enough. I'll let you figure out. But when you establish bijection, you also prove that it's sufficient. So you prove both that it's sufficient and minimal sufficient because this is in bijection to the entire function. Okay. You give me a parabola like this quadratic function, I can recover that coefficient here. And if I have this, I can just plot this entire function. I don't need anything else. It's like a smooth, very a quadratic, it doesn't have that much information. Sounds good. So you get sort of the idea of sufficiency and why the likelihood here is like, although it's an entire function, it doesn't carry much information. Because something like that sum is enough for me to know everything I know. I want to know about theta from this model. Good. Questions? Yes.
What do you mean by if I know this sum, I can construct the function? Like you could know the functional form, right?
I know the functional form because I know that I'm in this family. So what I know is, I know the f, I know beta, I don't know theta. Right? I know the family. That's my knowledge. So from this, I know everything here, right? I know this and I know this beta, right? But I need this to be able to like to cover the entire likelihood, or not likelihood up to a shift. Or the likelihood itself up to a multiplication factor. Without this, I can't reconstruct it, but with it, I can. Assuming that the model is correct.
That is quadratic because you know the quadratic from exponential time.
Not the exponential family, just the exact, we know the exact model, right? This is the model. I've specified the parametric model. So this is minimal sufficient for this parametric model, not for any model, right? Not for any exponential families, we'll see. Okay. Good.
That exponential term is a minimal sufficient statistic because it's a likelihood ratio, right?
Which one?
You say that our theorem is saying that following is the minimum because it's
Yes, because this is the likelihood function up to a constant. Yes, yes. Yeah, up to a constant basically means we don't care about constant, but this is like a likelihood up to a constant, and so it has to be minimal sufficient. Right? Yes.
About the other minimal sufficient statistics, if you're supposed to be able to distinguish between any 2 points of the likelihood function, why isn't your level set to get coarser?
No, not the likelihood function. You're not supposed to be able to distinguish between any 2 points of the likelihood function. The statistic has to be able to. So the statistic, not the likelihood. We're talking about this part, right? Where is it? This one, right? Why it doesn't show up? Sorry, let me see if I can. I think I lost the connection here. Yeah, you talked about.
Yeah, so the likelihood, or the vector of likelihood ratios, rather, if you have another sufficient statistic, and it's.
Yeah, it's talking about distinguishing between the data points, like here are the sums, right? If I have 2 observations, like summation of xi and summation of yi, right? If the likelihood, let's say, is the same for both up to a constant, then these sums have to be the same. It's sort of true here because these quadratics, if let's say quadratic is the log, so if quadratics are shifts of each other, then the shifts are along the y-axis. Then the location of the minimum doesn't change, and the location of the minimum specifies the sum. So 2 data points will have the same sum if and only if the quadratics are like shifts of each other. So that's what it's saying.
But I guess I don't know how you go from that to saying then the level sets of one have to be necessarily coarser than the other. Because I sort of
That's like a mathematical sort of thing that doesn't have anything to do with likelihood. So if I have 2 functions of data and one is a function of the other one, there's like a composition going from x to, let's say, t, and from t to l, right? There are like 2 functions here, and then there's another direction. So you can verify for yourself that the level sets of one has to be included in the other. It's just a mathematical idea. If a function is a composition of 2 functions, then like the incoming ones, the one that come from the domain, one has to have a smaller level sets. This is you have to like do
if it
something.
would just be the identity.
Sorry.
If it didn't do that, it would just be the identity function applied to it, right?
Not necessarily. I didn't. So let me maybe try to do a. I'm trying to let me try to reconnect because it seems like I lose connection. I don't know why. Doesn't know.
Recording in progress.
Okay, let me show you some. So we want to show that T is a function of L, right? So we want to show something like that. So is it showing up? Yeah. Okay, so what we can do is, suppose I have, this is my input domain, let's say. And then I have another domain here, another one here. So now I have, let's say, A, B, C. This is the X domain. These are my observations. And so both of, let's say T is, let's do this. So L maps, so this is my L. So maps X to, let's say, reals, let's say. 1, I don't know, 5, 7. Okay, so this maps these two to 1, and this one to, that's 7. Let's say we don't care about the 7. So 1 and 5 here. Okay, that's my L of X. And then I have another T of X. So, so here, for example, L of A is equal to L of B. Right? Now I want to say I have another one, which is, let's say 1.2, 1.4, 1.6. So now my T, for example, is like this. This goes to that. This one goes to this. And this goes to that. Okay, so that's T of X. That's X to reals. So can this T be a function of L? Does this imply that T of A is equal to T of B? So this doesn't imply it because they go to different things. And you can see that I can't write T as a function of L, because if I want to write T as a function of L, I have to map this to at most one point. So there is no function such that T can be written as F of L. So T of X, the point is this, T of X cannot be written as T L of X for all X. Because if I can do this, so both A and B have to go to, because they go to the same place here, whatever this is, and then like one or, and then T takes one of them to something else, so you can have. But if in the other direction, if T is like that, so for example, if T, for example, takes both A and B to this guy, right, and this guy can go anywhere at once, then there is a function. Okay, so this condition now holds, right? Because whenever L, A, and B are equal, then T, A, and T, B are equal, right? So this holds. So there is a function and you can find it. So what is that function? The function is, if I map 1 here to this and 5 here to that, that's my F. So I can construct a function that does that composition. Okay,
Yeah.
does that make sense? Okay, yes.
So maybe a point of clarification, because if I'm understanding this correctly, in this case, the entire parabola is a single value of the function L.
Yes,
Right?
yes.
So like L is not, like the parabola is not L, the parabola is a single value of L or one. Like,
Yes. Basically,
so like the level sets that we're talking about have nothing to do with.
no, the level sets have nothing to do with the level sets of this. Yeah, so
Yeah.
this would be, this would be 1, let's say for particular X, that would be like L of X. L of Y in this case would be this guy. It's going to be shifted. It's actually log of this. So this is log, if you want. This one would be log of L of Y, and they all like going to be shifted along the same line. So if that's the case, then well, actually this is not L, this is That's a bad idea. Because that L is like the likelihood ratio. So the likelihood ratios would actually be the same. Sorry. Yeah, but this gets to the point. That capital L that I had would be the same for both, because this is like Lx of theta. I'm gonna write it like that. This would be for any other x that have the same sort of, this would be like Ly of, if it's shifted, then both of them will have the same L of x. So they would coincide. So if I want to do, so both would be like this, and the other one would be on top of this. So that's Lx equal Ly, the entire function. And that's the case, then x and y, sorry, then this means that sum of xi has to be equal to sum of yi, and this is the case because they are sort of shifted versions of each other. They have the same location at the minimum. Yeah, that's a good point. So the entire function is what we're looking at, you're not looking at this function. So not the level sets of this function. Yeah, sounds good. Just getting a little bit of like used to the likelihood being itself, the entire function being a statistic is a little bit, it takes a little bit of thought, okay, to get comfortable with. That's why I do simple examples A, B, C for functions. The space of these likelihoods is like a space of functions, so I can't represent that. Okay. Just think about it. If you have questions, we can come back again. There is something a little bit deep going on here, which we'll see. And that's the case with the second example. So if you have the Laplace location family, exactly the same thing. I just drop this 2 here. If I drop this 2 here, now my base density looks like this. If you plot it, it would be like this double exponential, right? That's f of x. There's like a kink at 0. It's not a smooth. And if you write down the likelihood, it would look like this. It's very similar to that, right? What we had there. And then I can apply the log and the negative sign. I get that this function, theta maps to this. This is minimal sufficient, okay? I can't, like, there's no squaring it to simplify. So I could have said, for example, at this point, in this case, it would be, I mentioned it here. So this is minimal sufficient, but there is more, like, this is enough, but I can like do a little bit of calculation to show that this is also bijected to summation of xi. Here, this is minimal sufficient in the first step. And it doesn't look like that it simplifies. So far is it clear that this is minimal sufficient? This function is, entire function is minimal sufficient. And the claim is that there is really not much reduction beyond the order statistic. That's what I wanted to maybe show by this. So if you believe that this theta maps to summation xi minus theta, this function is minimal sufficient. If I plot this, what happens is there is going to be, do it for yourself, like take a bunch of xi's and then plot it. You'll see that there's going to be kinks at the locations of, let's say, unique values of x. So let's say all the x's are unique. If you draw from this with probability 1, it's going to be, all of them are going to be unique. And these kinks would be these locations. Okay. So now the claim is that if I have this shape, if I give you this shape, you can read off these values, because you can go and look at the location of the kinks. It has that information. I can't recover the original data because I don't know if it's the first one that I see, whether it's x2 or x1. I just see the first, like, smallest one, and then the second smallest one, and the largest one. So I can recover the original data up to the order. I can't recover the order. And if you give me the order statistic, I actually just reconstruct this function. You can just easily plug it in and apply it. right? So there's a bijection between the shape of the likelihood or the likelihood, let's say the log likelihood up to it. I can't recover the exact like height of it. It can be shifted down or shifted up. That's fine. If you give me the shape, I can't tell you. I actually don't need the information to tell you how high it is. That's not informative. But this shape would produces this, and if I have these, I get that. So there's this bijection. So we showed that minimal, the order statistic is minimal sufficient. Okay, in the Laplace case. So you can see also that like the non-smoothness sort of causes it. The fact that the density is non-smooth means that you can't compress your data further. So the smoothness here sort of washes everything out. So the summation is enough to just do this, but this L1 sort of has more, in a sense, information. The likelihood of it has more information. Okay. Is it clear? There's a bijection between this function and those locations up to the shift. Okay. Sounds good. So you're now experts in minimal sufficiency, I hope. And you can do all the other exercises and things like that. These are the two extreme cases. So pause here a little bit, see if you have questions. Yes.
The ability here to like recover the order statistics is like good, but it only comes into the way the problem is set up, right? Like if they weren't.
Whether it's good or bad, I don't know, but yes, it comes up from the fact that it's caused by the way that you set up the likelihood. Like the problem is specifically are drawn from this parametric family. So this parametric family, the shape of it causes it. You can see the only difference is that I just changed the f of x. Both are location families, but somehow this family, in a sense, is more informative. Not more informative, it's hard to say, but yeah, more is, it's just, if you think that the sum of xi's is more compressed than the order statistic, then this has more information. You can't just, based on a sample of size n, let's say there are loss functions that need this information. Like you can set up decision problems in which this is needed. Like there could be some estimator that uses all the data. Sufficiency means in the first problem, the decision, whatever decision problem you set up, whatever loss function you care about, that is enough. So you're not going to lose the information in the model. So you go back to the idea of sufficiency. You can reconstruct basically the data up to like statistically equivalent data using this in this case and using the sum in that case. Sounds good.
A quick question.
Yeah.
What's the difference between the order statistic and the whole data? If we don't order it and we order it, what's the difference between these two?
Okay, anyone? So the question is, what is the difference between the order statistic and the whole data? Okay, what is it? Anyone? I mentioned that. Okay. So there is a loss of information. I lose something. Let's see if anyone remembers. Yes.
You lose the rank.
Yes, you lose the rank. So for example, like x1, x2, x3, 1, 2, 3, 3, 2, 1, 1, 3, like 2. All of these have the same order statistic, which is 1, 2, 3. Like this is x1, x2, x3. So when you say order statistic, it means the smallest one is 1, the biggest one is 3, and the middle one is 2. Right? I can't tell you which one of this happened in the actual case. Okay. Okay. Yeah. So you lose the rank. Rank means, for example, which data set, which data point was the minimum. Here, this was the rank would be 1. Here, the rank would be like 3. Here, the rank would be 1 again. Right, so you lose the rank. But the other way around. See, actually the other way around. So the rank of x1 is where it is, I believe. But you get my point, right? So you can't recover. You can't say, for example, whether x2 was the first, like the smallest one or the biggest one. The other way around. Any other questions? Everyone is happy? Okay. Now that you're happy, one last slide before, maybe 2 slides, but this is an example to see what happens if you don't have a common support. This example is from a homework problem in Layman's book, Theory of Point Estimation. I'm going to refer to it as TPE book. So consider a case where we have a family that has 3 elements, P0, P1, P2. So that's the parameter space. You can just think of it as ABC or 0, 1, 2. That's omega. It's sort of like a hypothesis problem with 3 possibilities, if you know hypothesis testing is. So the densities or the distributions are given by these expressions. So P0 is uniform in -1 and 1. So that's the density. P1 is uniform in 0 to 1, again 0, 1, and this is 1. And the last one has that density with respect to the Lebesgue measure. So like 0, and it goes up to at 1, and then it would be like 2 here. And you can verify that the 2 is there to have the normalization. Okay. The area under this has to be 1. So we have these. So the statistical problem is I get one sample from this probability model. Remember, there's an observation X. So X is distributed like P theta. I don't know which theta. So I don't know which one it is. I just get one observation. I have to decide which one it is. Okay, that's the decision problem. Okay. So let me maybe, I wish I could hide the answer. So let's sort of try to hide it. So remember what the last one was. So what do you think would be sufficient, minimal sufficient here, sort of? So let's say it was just 2 between these 2. The issue is that they don't have common support. They actually have disjoint support. So if my decision problem was between these 2, what would be minimal sufficient? So can you say it louder?
If the data point is positive or negative.
Okay, yes. So basically the sign of the data point is enough. Right? We don't need to know the exact value. If I just know that if it's positive or negative, it's enough to actually perfectly distinguish these. So it's sort of clear that sign of X would be minimal sufficient. But let's say if I have this information, not the information, but I just have this one as well to distinguish. Would the sign be sufficient? No. Why not? Like intuitively, why not? The sign wouldn't be sufficient in this case.
If it is positive, it could be from either of those.
Yes, if it's positive, it could be from either of 2, but okay, so maybe that's the ambiguity that I have to like be content with. Is there more information from the data? Like, do we get more information? Sorry? If it's greater than 1, that can happen. So it's gonna, we know that we made something like model is not wrong, so we have to go back. Yes.
Maybe like the discontinuities.
The discontinuities. Interesting, but it's not going to help. So if you get a data, the discontinuities would just tell you that in this case that these don't happen. for this particular case, right? So you're never, you can recover discontinuities before seeing any data in this case. But the discontinuities are not informative about, actually, is it informative or not? Maybe I should correct myself. Let's say the discontinuity at 0 is informative. The discontinuity that's captured in the sign. Okay. So this discontinuity is informative, sort of, if you want to say, and that's just captured by the sign. This one is not, because like all of them are 0 after this. So
Okay.
there's no information here. But there is more information in the data. Yes.
I think if it's closer to 1, it's probably more likely to.
Great, yeah, so because this is like putting more mass near 1. So if you're very close to 1, you're more likely to be from this than this. So statistically, this is more probable, more likely. Okay, I want you to just understand intuitively what happens. So you can distinguish this perfectly, and that's where statistics comes in, but you can sort of distinguish to some extent. Okay, to the extent that's possible, but your data has information in distinguishing these two, even a single data point. And if you just take the sign, you would lose. So if I am closer to 1, I'm more likely under this. And this is captured exactly by the likelihood ratio. If you take the likelihood ratios of like P 2 to P1, then you can see the likelihood ratio would be like when likelihood ratio is bigger than 1, tells you that like the evidence is in favor of P2, right? And it will be bigger than 1. So you can check when this is, so at 1/2, after 1/2, I believe this is going to be bigger than 1, so it's more informative. It's more likely to be under P2 than P1. So the point is that this likelihood ratio tells me something, okay, carries information, the likelihood ratio. So if I took let's say P0 as the base, right? So if you follow through what we did, we took one of these parameters, let's say theta naught or P0 as the base probability distribution or the probability density, and then form the likelihood ratio with respect to that. If I form the ratios, basically what I get is that for both of them, P1 relative to this and P2 relative to this, they're essentially the same. 0, so you get here. 0 here, because they're both 0 here, divided by 1, so you get 0. And then infinity, basically. This divided by that, this divided by that is infinity. So this just has the sign information, basically. Infinity is fine if you're okay with infinities. This is saying that there are infinite information here, infinite evidence, basically in favor of P1 and P2. So this is being bigger than 1 means better evidence for P2 against P0. And what this is saying is that if your data is in 0 to 1, P2 or P1 is infinitely more probable than P0, which is reasonable. But they both carry the same information, and it's just a sign. This is the sign. This is like step function 0 to infinity. So this likelihood ratios carry the same information as the sign. If you do this in this DCS family, you lose information. So you have to also look at the likelihood ratio between these two. So if I put this, and this together, then all the pairwise likelihood ratios, then that would give me a sufficient statistic. Okay. And you can think about what this is saying. This is just equivalent to just whenever X is positive, keep its value. Whenever X is negative, discard the value. That's your sufficient statistic. You can write it in different fashions. So X plus if you want, and indicator X negative. So you can write it as like this 2 point statistic. This keeps the sign, this keeps the positive value. This is 0 or the positive value if X is positive. Or you can just say that this is also a function of this, so this and say X plus is sufficient. So at the end of the day, X plus is sufficient, which is just X if X is positive, 0 otherwise. So you just truncate your X. When it's negative, otherwise keep it. Yes.
If it's not DCS, you took P2 would be 1.
So this is an example of what you have to do. That it's not general. There is like a tier, like a problem in TPE. Sometimes I assign. So basically, anywhere that they differ. So whenever all of them have 0 support, you don't have to worry. Right? In cases where you have like mismatch support, then you have to consider all the possible like the ratios. You can't like keep one base one. You can see what goes wrong here. Right? There's a formal way of writing it. If you're really interested, I can assign it. It's a hard problem. Let's see how. I can ask like, or I can assign it. Whenever someone asks about this, I'm gonna assign it. You can choose to not do it. It's a fun problem. But it gives you a recipe for what you do in general. Does that make sense? If you think about this, it's interesting, fun example, and it shows you the statistics, what is like statistics is doing. So it just squeeze the data so that every bit of information is, that's what a statistician would like to do. Squeeze it until there is no more data. Okay. And there is data here, so if you want to distinguish between, you can't perfectly distinguish, but statistically there is information. So you want to squeeze that out. And this idea that likelihood ratio is evidence of one model against the other comes up a lot. We may see it later. Sounds good. Yeah. Questions? We have time for one more slide. Just want to introduce this idea of empirical distribution. How many people know what empirical distribution is? Heard about it? What is empirical? Okay, maybe. Or you first.
Just take the data and do the calculate the moments you get.
Moments?
Yeah.
What kind of moments?
Maybe sample.
Oh, a sample mean. Those would be empirical moments, right? But the empirical distribution is a little more general. You can recover like sample mean would be the mean of the empirical distribution. Sample moments would be the moments of the empirical distribution. But let's see, what is your idea of empirical? Yeah, it's written there, unfortunately.
Measures over the data.
Yeah, so exactly what I wrote there. Formally, it's a discrete measure that puts mass 1/n at the points that you observe data. So you have the data points, and so let's say I have this is my data set, right? I'm gonna go put a mass of we have 1, 2, 3, 4, 5. How many there are? 7. So I'm gonna go, the first one is 0. I'm gonna put mass 1/7. The first one is actually -1 here. And then 0, actually, yeah. Yeah, it's a little bit hard. So let's do this. 0, 1, 5. That's my data set. I'm gonna put mass 1/3 on 0, 1/3 on 1, and then 1/3 on 5. 2, 3, 4. Okay, so it's just a probability measure if you know probability measures. It's just a discrete probability measure that has these point masses. Okay, oftentimes written as this delta x. So it's in this case, it would be like 1/3 delta 0 plus 1/3 delta 1 plus 1/3 delta 5. So it's in general 1/n summation of these Dirac, sometimes called Dirac measures or point mass. Again, if you remember what the measure is, it's just a set function. It assigns to every possible sort of measurable set a number, which is its measure. So this is just assigning this value. For every set A, if it contains X, you get 1. If it doesn't contain X, you get 0. So if this set the measure of this set is 1 under this measure, the measure of this set is 0, the measure of this set is 0, the measure of this set is 1. So it models the probability distribution of a random variable type that takes value x with probability 1. So this would model the probability distribution of a random variable that takes value 0, 1, and 5 with equal probability. Okay, in general, this models the probability distribution of a discrete random variable that takes these values with equal probability. Okay, it's a random measure because the data is random. It's a function of the data, but it just captures the information in data. But there is a bit of loss of information. One thing the first thing that you notice is if I go from this to that, I lose the order. Okay, this measure loses the order. I can't tell whether this, for example, again, x being 5, 1, 0, captures the same sort of, like has the same empirical distribution. There is more loss of information if there are repeated values. You can see here, if there are repeated values, it's actually not that much loss of information. Not loss of information, there's more intuitive compression, but there's no loss of information. I can still say there is 1, 1, negative 1, there's 1, 1, and 3 zeros and 2 fours because of the relative heights. Sort of in the end, the point is that this is going to be minimal sufficient in the not minimal sufficient. It's going to be sufficient in the IID case. Okay, and I'll come back and continue because it's important. Okay, just keep in mind this for the next time. We'll talk about this. Thank you guys. See you next time.